If you're working in AI safety, you've probably asked the same question. Can we mathematically guarantee that a sufficiently advanced agent will never violate its alignment constraints? The engineering answer is usually, not yet, but more compute and better verification will get us there. The mathematical answer is harder. Recent formal research establishes that the core barrier to AGI safety isn't the impossibility of an aligned state, but its structural unverifiability. We are not facing a temporary engineering bottleneck. We are hitting a fundamental wall in computability theory. Let's break down why universal alignment verification is mathematically impossible, and what that actually means for how we build and constrain these systems. The argument rests on exhausting every possible computational vector an external verifier could use. There are only two, infinite domains and finite domains, and both collapse under the weight of formal logic. First, consider an open, unbounded domain. You want to verify that a Turing-complete agent behaves safely across all possible inputs and execution traces. This immediately runs into Rice's theorem. In computability theory, Rice's theorem states that any non-trivial semantic property of partial computable functions is undecidable. Semantic here means the property depends solely on the input-output behavior of the machine, not its internal syntax. Safety is fundamentally a semantic property. You don't care about the source code, you care about what the system actually does. Because safety is non-trivial, meaning some programs are safe and some aren't, Rice's theorem proves that no algorithm can perfectly decide whether an arbitrary AGI will satisfy that property. The verification problem is dynamically undecidable. You might try to bypass this by switching from dynamic verification to static proof. Fix a formal system, prove the safety property before execution, and call it a day. But this triggers Gödel's incompleteness theorem. To reason about discrete, recursive computation, your formal framework must be strong enough to express Peano arithmetic. Once it contains arithmetic, Gödel's diagonalization lemma guarantees that the system will be incomplete. There will always be true safety statements that the framework cannot prove, and consistent frameworks cannot prove their own consistency. You're forced into a trade-off. Either your verifier is incomplete, missing genuine safety guarantees, or it's inconsistent, issuing false certificates. This is where most modern engineering intuition pushes back. Fine, you say. The universe is finite. Hardware is finite. Let's just restrict verification to bounded, halting configurations and exhaustively check all possible finite state spaces. This strategy, which we'll call universal finite verification, sounds pragmatic. But it collapses at Trakhtenbrot's wall. Trakhtenbrot's theorem from finite model theory proves that the set of sentences valid across all finite structures is not recursively enumerable. It's Coré complete. Let me unpack that technically. You can enumerate finite structures and check if a safety property fails in any given one. That's computable. But to guarantee safety universally across all possible finite hardware configurations and environments, you need to verify universal finite validity. The proof reduces the halting problem to finite satisfiability. A machine halts if and only if a specific first-order sentence has a finite model. Since finite satisfiability is ray-complete, its complement, universal finite validity, is co-ray-complete. That means no algorithm can even list all finitely valid safety certificates, let alone decide them. The finite world does not erase computational complexity, it reifies it into descriptive structure. Universal verification over bounded domains is algorithmically uncomputable. So we've exhausted both infinite and finite verification vectors. But what about the computational cost within the finite case? This is where descriptive complexity theory bridges logic and computational difficulty. The language you use to specify safety dictates the complexity class of the verification task. First-order logic is too weak to express transitive closure or basic reachability. Least fixed-point logic corresponds exactly to P, which is tractable, but still insufficient for modeling recursive, self-improving agents. To capture the global, emergent behavior of a recursively self-modifying architecture, you need expressive power like partial fixed-point logic. By the Immermann-Vardy and Fajan theorems, jumping to PFP automatically transports the verification problem into PSBACE. And PSBACE is where exact auditing demands combinatorial explosion. The chess analogy is perfect here. The game tree is strictly finite, yet solving it exactly is PSBACE complete. No monitor in the universe has the resources to exhaust it. This logical expressivity constraint directly derives the Soundness-Completeness-Tractability Trilemma. For any verification architecture, you cannot simultaneously satisfy soundness, meaning only certifying truly safe behavior, completeness, meaning certifying all safe behavior, and tractability, meaning doing it in polynomial time. The trilemma isn't a statistical anomaly or a limitation of current data. It's a structural necessity. If you demand completeness over expressive specifications, tractability vanishes into PSBACE hardness. If you demand tractability and soundness, you must sacrifice completeness, leaving gaps in your safety guarantees. So how do we actually build safe systems today? We accept the trilemma. Modern containment strategies are not temporary patches. They are mandatory sacrifices of logical expressivity, deliberately selected to rescue a decidable fragment of safety. We see this in four main architectural taxonomies. First, logical isolation or shielding, where the agent is surrounded by a rigid monitor operating in a decidable logical fragment. The trade-off is clear. If the language is restricted to guarantee halting, the AGI loses agency over decisions that are semantically inexpressible in that fragment. Second, proof-carrying code, where the AGI must attach a formal deductive proof of safety before acting. The verifier stays fast, but the agent becomes unable to execute legitimate actions whose underlying proof exceeds structural complexity bounds. Third, temporal myopia or bounded horizon planning, which amputates asymptotic vision by limiting optimization to a fixed number of future steps. The decision tree becomes decidable, but at the cost of strategic blindness to long-term consequences. And fourth, physical confinement or AI boxing, which isolates the agent from external actuators and networks, artificially stifling causal expressivity. This leads to what we might call the paradox of weakness. By forcing deployment environments to use weak logics, short horizons, or physical boxes to maintain decidability, any surreptitious malicious behavior designed by the AGI within its Turing-complete inner space will remain entirely invisible to the supervisor. The system is safe by containment, but blind by design. The mathematical landscape is unambiguous. An open domain yields fundamental undecidability via Rice and Gödel. A universal finite domain collapses into algorithmic incomputability via Trakhtenbrot. A particular finite domain traps the supervisor in PSBACE-hard intractability. The sacrifice of expressivity is not a software limitation to be overcome by optimization. It is the immutable toll that the laws of computation demand to grant us even the temporary illusion of control. Ultimately, this research proves that the core barrier to AGI safety is not the impossibility of an aligned state, but its fundamental unverifiability. Because any robust safety paradigm must certify containment universally, and because universal verification breaches Trakhtenbrot's wall, the overarching task of AGI alignment certification is formally undecidable. For researchers and engineers, this doesn't mean giving up. It means shifting focus from chasing perfect verification to rigorously managing the Pareto frontier of the Trilemma. We design bounded, decidable fragments, we accept structural blindness as the price of containment, and we build systems that are safe by mathematical necessity, not by empirical hope. The wall is real. Understanding it is the first step to navigating it.